moving, continuing straight on. So we were saying at the end of the previous session, L squared, S squared hat, the operators, LZ hat and SC hat, they all commute with the Hamiltonian operator now with the spin orbit term dropped out, so the third term drops out. And with that modified Hamiltonian with the first, second and fourth terms in it, when you solve the eigenequation, you get the eigenenergies turn out to be this. Now, you've already noticed lately there's quite a bit of hand waving. You're getting quite a lot of ICBST. It can be shown that. And remember, this text is a sort of an overview, an introduction to what quantum mechanics is. So as we get towards the end of this course, things inevitably get harder, of course. And what's happening is that Davies and Betts, two authors, effectively, in a manner of speaking, you can say they are now, towards the end of the text, they are flying over the icebergs and pointing out, there's an iceberg, there's one. And you probably know that about 90% of an iceberg is under the surface. You only see about 10% of the total volume of the iceberg. So you're getting a taste of what quantum mechanics can do, but you're not expected to understand or to be able to do the full details. So that's sort of normal. You're getting an overview of the field. All right. So deriving something like this, these eigenvalues for the energy, in the case where the third term, the spin orbit coupling term, has been neglected due to the much larger impact of the fourth term, the Zeeman effect with large magnetic field, because we're talking about that case. So these are the allowed eigenenergies, and here's the term that comes from the Zeeman effect. Now in 2 sessions back I was talking about this term, and I was asking you to keep it in mind because we would be talking about it in the future. Well, the future's now. Okay. Now you may also remember me talking about in the case of the strong magnetic field, there were 5 allowed energies. The energy split 5 ways, and the spacing between, the difference in the energy levels, allowed energy levels in those splits, were all equal. Now you can see that now from here, because assume the magnetic field's constant and the Bohr magneton, that's constant. So there's just a constant, right? So the difference in the energy levels will be just some multiple. These turn out to be integers. I'll explain in a minute. They can have these allowed values. I'll explain that soon. So the difference in energy levels will just be this much, right? So these are integers. They step up in units of 1. And therefore this energy is increasing by this amount, okay? Constant at each level, for all 5 levels. All right, so what are these values? Well, we've been assuming that L is 1. Okay, now this, so if L is 1, and M can be plus minus a half, right? So the text is saying there are 5 possible values for this. Now, does that make sense? How can that be? So if L is 1, ML, remember this is the component of the orbital angular momentum, L, along the z-axis. So so this can range, M can range between L and minus L. So that's between 1 and minus 1. So 1, 0, minus 1. Right? So the possible values of this are plus 1, 0, minus 1. Okay? A similar story for S. It can range between plus a half and minus a half. Right? So so the 2 of MS ranges between 1 and minus 1. And this ranges between 1, 0 and minus 1. So together, you add the two, the whole thing ranges between plus 2 and minus 2. So in steps of 1. So 2, 1, 0, minus 1, minus 2. 5 possibilities, and hence this energy splits 5 ways, depending on this value. Okay? So that clears up quite a bit of the mystery of 2 sessions back in that diagram, the splitting diagram that I was showing you, and referring you to this 2 sessions back. So hopefully now you can go back 2 sessions and make more sense of it. All right? So those energy gaps, between those 5 levels is this amount. It's constant, right? Spaced by this amount here. Okay. All right. So that's case 1 we've been talking about. Now case 2, called the Paschen-Bach effect. 2 guys who investigated, I presume. In this case, you do not neglect the spin-orbit coupling effect, right? So that makes things quite a bit more complicated. Now, so we're going to use what's called first-order perturbation theory. Now we haven't done that yet. It's a bit of a chicken and egg thing. You can't understand it until you've done chapter 10, but you can't understand chapter 10 unless you've done chapter 9. So it's a bit of a catch-22. Anyway, so when you have done chapter 10, please come back to this at chapter 9 and look at this with a fresh light, in the light of the knowledge you will have gained from studying chapter 10, the next chapter. Right? But for the moment it's just being thrown at you. So you will use a technique that's called first order perturbation theory from chapter 10. Chapter 10 is about perturbation theory. And what's perturbation theory? What does it mean to perturb? It means to add a small term to the Hamiltonian. That will change the eigenfunctions a little bit. It will change the eigenvalues a little bit. And there are orders of perturbation, those changes. They're like first order changes and second order changes. The second order changes are much smaller than the first order changes. So a first order perturbation theory is the theory about the perturbations of first order, the smaller ones. And second order are much smaller. You can tend to neglect them. Right? So what we're doing here is when you perturb something, put the emphasis on the something. You're taking something and changing a little bit. So the something that you're changing, that's sort of your reference point, if you like. So in this case, what we're modifying or perturbing or changing is the previous case when the magnetic field strengths were very strong. Okay, so in a sense, the Paschen-Bach effect is what you get when you perturb the strong field effect. So case 2 is tweaking, modifying, perturbing case 1, right? So what you're doing is you will have changes in the allowed eigen energies, the eigenvalues for the energy, and these are the eigen energies for the strong field case, and these are the eigen energies for the Paschen-Bach, right? And this is the difference between these. So these are your corrections to the energy. So this is the strong field case, and this is when you add the